This section introduces the spanning tree protocol in support of multi-switch networks. As the enterprise network expands, multi-switch networks are introduced to provide link layer communication between a growing number of end systems. As new interconnections are formed between multiple enterprise switches, new opportunities for building ever-resilient networks are made possible. However, the potential for switching failure as a result of loops becomes ever more likely. It is necessary that the spanning tree protocol therefore be understood in terms of behavior in preventing switching loops and how it can be manipulated to suit enterprise network design and performance. So upon completion of this section, it is generally expected that trainees will be able to describe the issues faced when using a multi-switch network, explain the loop prevention process of the spanning tree protocol, and configure parameters for managing the STP network design. Enterprise networks generally comprise of multiple switches that are used to support the sometimes large number of users that are physically connected within an enterprise. Switches, as we have seen, are tasked with ensuring that data is forwarded over the local network between end stations, or to gateways that allow the traffic to be forwarded to other networks. One of the main concerns of switching is that hosts connected to a switch that has only a single switching path to any other destination may become isolated from the rest of the network in the event that the switch upstream becomes inactive or there is a failure on the link. This is referred to as a single point of failure and may affect business performance and revenue. So in order to combat this, redundancy in the switching network is required, and the example that is shown here demonstrates how redundancy is applied. We give a common design here in which access switches in the form of switches C, D, and E are connected with two links to two switches in the form of switch A and B that are acting as aggregation switches for traffic transmitted between end stations and other locations on the network. Should either switch A or B or a link between any of the switches fail, traffic received from end stations connected to switches C, D, and E can continue to be forwarded with minimal impact to the network. The problem faced in a fully functioning network, however, is that traffic forwarded via one link may ultimately be received via the alternate link. This effectively causes switching loops to occur in the network that can drastically affect performance of operation and result in loss of data. The red arrows give an indication within the topology of one such possible path over which switching loops may occur. As we progress, we shall look in more detail at how forwarded traffic can cause such switching loops to occur. The use of redundant links in the network can generate switching loops through two factors. The first of these is due to broadcast in the network. We have explored how a switch will flood broadcast where the frame received is set to be broadcast to all destinations in a local network. The resulting flooding of the frame, which based on the example given here, originates from host A and is forwarded out of all port interfaces of the switch, which in this case is switch B, with the exception to the interface on which the frame has been received. The same process is then performed by other receiving switches in the form of switch A and C that will then complete a cycle of flooding back to switch B. This in turn will result in frames being flooded to host A and B as a result of the switching loop occurring in both directions, and in the case of host B, we can see that multiple duplicate frames are flooded to the destination. The other major issue of redundancy in the network is in the inherent MAC instability that occurs within the MAC address table. We can best demonstrate that using host A as the source of a frame that is to be forwarded to host B. In this instance, we should understand that switch B will record the MAC address of host A and associate this MAC address with the interface upon which the frame was received, which in this case is interface gigabit Ethernet 0/0/3. The switch, not having an entry in the MAC address table, will flood the frame to both switch A and switch C. Switch C will also flood a copy of this frame to switch A and host B. However, for simplicity, we demonstrate the flow only to switch A here. Switch A will flood the frame to switch B that will again record the MAC entry, but this time originating from interface gigabit Ethernet 0/0/2. Frames destined for host A from host B will be forwarded to switch C, and in this instance forwarded to switch B. Switch B, however, recognizes host A as being associated with interface gigabit Ethernet 0/0/2 and inadvertently will forward the frame to switch A, resulting in the frame never reaching the intended destination. The design goal that is faced is how can a switching network implement redundancy whilst also ensuring that such effects as we have shown do not occur as a result of switching loops. The answer lies in the logical management of traffic flow that enables only a single switching path to be active in the switching network at any one time whilst maintaining physical redundant links. This switching path is referred to as the spanning tree that is constructed through a protocol known as the spanning tree protocol, or STP. The example shows how an interface may be logically blocked in order to ensure only a single path between host A and host B can exist, thereby eliminating possible loops. The foundation of the spanning tree is the establishment of a root bridge from which the tree architecture is formed. This is represented by a single switch in the network from which all other switches are reached. These switches are considered to be non-root bridges. The term switch and bridge may be used interchangeably here. From the root bridge in this example, we can see a general inverted tree structure has been formed and is represented by the solid lines, whilst all other links that are capable of generating loops may be logically blocked. We may then ask, how exactly is it determined which switch in the spanning tree topology will be considered the root bridge? This discovery relies on information contained within each switch known as the bridge ID. This bridge ID is comprised of two parts. The first is a priority value that is configurable within the spanning tree protocol configuration and represented as an integer value in the range of 0 through to 61,440, but can only be represented in increments of 4,096. By default, this value is 32,768. The second is the MAC address of the switch. The root bridge is determined by the smallest value. A smaller priority than all other switches will determine the root bridge. If, however, two or more switches have the same smallest priority, the unique MAC address with the smaller value will determine the root bridge. This example shows the root bridge, and in this case is determined based on the priority that has a smaller value when compared to all other switches of 4,096. So how exactly do switches learn information about the neighboring switches? Well, communication within the spanning tree protocol relies on a special frame known as a bridge protocol data unit, or BPDU for short. Its purpose is to share spanning tree based information with neighboring switches to allow the spanning tree to be formed and maintained. In the spanning tree protocol, there are two forms of BPDU that are generated. The first is the configuration BPDU that is generated by the root bridge and propagated downstream to all other non-root bridges. This allows all downstream switches to be aware of the root bridge and to inform that the root bridge is present and active within the spanning tree network. Once the downstream switches receive the BPDU, the switches will propagate the BPDU to all other switches further downstream. The second BPDU is generated by downstream switches and propagated upstream towards the root bridge and is known as the TCN BPDU, which we shall introduce in more detail shortly. Every switch interface that is part of the spanning tree topology is assigned a path cost that represents the cost of transmission over the link on which a BPDU is received. This is demonstrated here, in which all interfaces on which BPDU are received are associated with a cost value, in this case of 20,000. Within the BPDU is a field known as the root path cost, or RPC, that is used to measure the cost of a path back to the root bridge, for which the path cost acts as a measurement. The root bridge is always considered to have a root path cost of 0, since it represents the base of the spanning tree topology. As BPDU are propagated to the peering downstream switches, the associated path cost of each receiving interface is added to the root path cost found in the received BPDU. This then represents the root path cost for the switch. BPDU are then propagated further downstream, carrying the new root path cost for which the same process occurs. The purpose of the path cost is to determine metrics that make up the root path cost, which defines the shortest path for each switch back to the root bridge. In the case of the left downstream switch, two BPDU will be received, one with a root path cost of 0 and another with a root path cost of 20,000. The switch will accept the BPDU with the lower root path cost after adding its own path cost as the shortest path to the root bridge, and shall propagate the BPDU downstream based on this value. There are a number of standards available to represent the path cost for the interfaces on which BPDU are received. This table represents those path cost standards that are supported within the VRP operating system. The default standard supported, however, is the 802.1t standard, since the larger values provide a more accurate metric for measuring the path cost of each interface and leaves room for expansion on the metric values used as port speeds increase. We should also mention that the 802.1t standard is equivalent to what is now known as the 802.1d 2004 standard. The establishment of the spanning tree also defines the need for port roles to be assigned to each of the port interfaces that are participating in the spanning tree topology. There are 3 port roles used within the spanning tree protocol. For every link between 2 switches, one of the 2 switches will be responsible for the propagation of BPDU to the other switch. The switch on each link with this responsibility is considered the designated switch for the segment. The port interface over which BPDU are propagated is called the designated port. The root bridge represents the top of this structure, and therefore all ports of the root bridge are designated ports. As such, BPDU are always propagated via all spanning tree ports on the root bridge. The switch downstream of the designated switch for the segment will receive the BPDU. The interface on which BPDU are received is known as the root port, since it is considered the port that represents the shortest active path back to the root bridge. In the example given, the switch that receives 2 BPDU will only assign the interface with the lower root path cost as the root port, as it represents the shortest path back to the root bridge. For ports that are neither considered root ports nor designated, these ports are referred to as alternate ports and should only receive BPDU, but shall not play an active role in the spanning tree topology, since frames cannot be forwarded by an alternate port. Where redundant links exist between the same 2 switches, as demonstrated in this example, the root path cost is likely to be equal, and therefore cannot be used as a means by which to determine which segment represents the active segment and which interface should take on the role of an alternate port. Each port interface is associated with a port ID, which again, like the bridge ID, is comprised of 2 parts. The first is again a priority value known as the port priority, and the second part is the actual port number. The port priority ranges from 0 to 240 in increments of 16, with the default being 1 to 8, for which the lowest priority takes precedence. If the port priority is equal, as we can see here, the lowest port number becomes the denominator for choosing the port to become the root port. The propagation of BPDU by the root bridge is controlled by a timer known as the hello timer. Each time the hello timer expires, a new BPDU will be propagated downstream, and this by default occurs approximately every 2 seconds. Downstream switches expect to receive a BPDU periodically to verify that the upstream path to the root bridge and the root bridge itself is still active. If a BPDU is not received in a defined period of time, the downstream switch will assume that failure has occurred upstream. The period of time that each switch will wait is based on 2 values. The first is a max age timer that by default is set to 20 seconds for all switches. The second is a message age timer. As BPDU are propagated downstream, they experience some delay of approximately 1 second. This propagation delay is factored into the message age and carried in the BPDU. As the BPDU travels downstream, the message age is incremented. Each switch will calculate the time to wait for a BPDU by deducting the message age from the max age. If we take an example of a downstream switch that has a message age of 2, we can assume that the max age is equal to 18. So if a BPDU is not received in approximately 18 seconds from the point of receipt of this BPDU, the path upstream will be considered by the switch to have experienced a failure. How the switch reacts to such failures shall be demonstrated shortly. We first take a look at the election process that occurs at the point in which one or more switches become active in the spanning tree topology. Every switch participating in the spanning tree contains a record of the root bridge and the designated bridge for the segment over which BPDU are to be received. For the root bridge, these 2 records will reference the switch's own bridge ID, since it is the root bridge and is also positioned at the top of the spanning tree hierarchy, meaning that there is no upstream switch beyond the root bridge. When switch is initialized for the first time, all switches participating in the spanning tree will assume the position of root and begin to advertise their position as such using BPDU. The result is an initial flooding of BPDU to all neighboring switches. The purpose of this is to determine the true root bridge for the spanning tree topology. Each BPDU initially contains the bridge ID of the ascending switch and the bridge ID of the designated switch for the segment on which the BPDU is received. This information is used by the receiving switch to compare the bridge ID of the neighboring switch to its own. If it finds the advertised bridge ID is of a lower priority, meaning the bridge ID is a larger value, the switch will ignore the received BPDU and instead continue to advertise its own BPDU to the neighboring switch. If the advertised bridge ID is of a higher priority, meaning the bridge ID is of a smaller value, the switch will cease to advertise itself as the root bridge. The bridge ID information will be changed to the bridge ID of the neighboring switch in terms of both the root and designated switch information. The switch will in addition begin to advertise BPDU downstream from the considered root bridge to other switches. The downstream switch will analyze the BPDU received and compare the root bridge ID that, in this instance, does not relate to the neighbor but to the upstream switch. The designated bridge ID, however, will still refer to the neighboring switch for this segment, since it is this switch via which BPDU from the root bridge are expected to be received. Again, if the bridge ID is better, the switch will conform and advertise on behalf of the upstream switch. If not, the upstream switches will again need to concede their roles as the designated switch and root bridge and conform to the new topology. Once it is determined as to which switch in the topology is the actual root bridge, it is then necessary for the port roles of all switches to be determined in order to ensure the stability of the topology. As we have mentioned, a switch positioned as the root bridge will assume immediately that all interfaces participating in the spanning tree process operate as designated ports. It is via these designated ports that BPDU are propagated downstream. The BPDU of the root bridge have a root path cost of 0 and are received by downstream switches. This is used to determine the root port for the switch in the event that multiple paths back to the root bridge exist. If we take switch B, for example, there are two paths via which it is physically possible to reach the root bridge. The path directly to switch A is represented by a root path cost of 0, but when added to the path cost of interface gigabit Ethernet 0/0/1, which based on the default 802.1 standard will carry a path cost of 20,000, will assume a root path cost of 20,000 via this path. For the path via switch C, the root path cost received is 20,000, and when added to the path cost of interface gigabit Ethernet 0/0/2, will give a root path cost of 40,000, which represents a less preferable path to the root, and so interface gigabit Ethernet 0/0/1 assumes the role of the root port via which BPDU from the root bridge are processed. Any BPDU received via interface gigabit Ethernet 0/0/2 will be received but not processed. The same negotiation process will also occur between switches A and C. The link between switch B and C will also go through a process of negotiation. In this instance, both switches assume the best path to the root bridge and attempt to assert themselves as the designated bridge for the segment. The BPDU received will contain the root path cost of 20,000 in both instances, which when added to the path cost for the interface gives a root path cost of 40,000 for both switches B and C. Since the root path cost is unable to determine the designated switch for the segment, the switches again must make a comparison of the bridge ID of the peering switch. We see here that the priority for both switches is the default 32,768. However, the MAC address of switch B is considered of a lower value and therefore holds a higher priority, thereby asserting switch B as the designated switch for the segment. Interface gigabit Ethernet 0/0/2 on switch B will therefore take the role of the designated port, while the interface gigabit Ethernet 0/0/2 on switch C, being neither a designated port or root port, will be considered an alternate port and as such cease to transmit BPDU. IEEE standards for the spanning tree protocol define a number of port states through which switches must transition in order to achieve a stable spanning tree topology and avoid switching loops occurring during root bridge and port row convergence. The example given here shows this state transition process and the possible states to which a switch interface is able to transition through. Any switch interface that is shut down is considered to be disabled and can be achieved at any point in the port state transition process. Once a port is enabled, however, it will transition initially to a blocking state, in which no BPDU will be forwarded but may be received. This also represents the state of an alternate port. The received BPDU will be used to determine if a state transition is to occur, in which case a state transition to the listening state will be performed. In this state, a switch may begin to transmit BPDU to neighboring switches, but not populate the MAC address table with any information, since time is needed to allow the topology to converge. This is managed by a timer known as a forward delay timer that specifies a period of 15 seconds by default to give enough time for all switches in the topology to converge. After this period, the switch will generally move into a learning state. It is in this state that the MAC address table can begin to be populated. However, the forwarding of data in the form of network traffic is still restricted. This learning state is also managed by the same forwarding delay timer, following which a forwarding state is reached and traffic can be transmitted within the switching network. We now take a look at the behavior of the spanning tree protocol in the event of failures to the network, and how these failures are managed. It is important to understand the way in which such failures are dealt with, since such failures affect both the topology of the switching network that may result in suboptimal switching paths and also incur a varied period of downtime for convergence. We firstly introduce what happens when the switch acting as the root bridge for the topology fails. In this instance, we can see that switch A is the root bridge and in its failure ceases to generate BPDU. The downstream switches, as a result of not receiving any BPDU, will see their max age timers count down, which may take up to 20 seconds. The variation here depending on the message age for the switch. Once the max age is no longer greater than the message age, the switch will assume the root bridge is lost and assert itself once again as the root bridge. The root election process will once again take place between the remaining switches, in this instance between switch B and C. From this point, a new root bridge is discovered based on the bridge ID of the two switches, along with the designated bridge for the segment, which in this case must again be the switch that is considered the root bridge. The switches must then go through the port state transition, which involves two periods equal to a forward delay period of 15 seconds by default, as the switch moves from listening to learning and finally to a forwarding state, resulting in a period of up to 50 seconds based on the max age and two forward delay periods. Recovery of switch A will again force reconvergence of the spanning tree, as switch A attempts to assert itself once again as the root bridge. Another form of spanning tree topology failure may occur on the downstream switch that experiences a loss of connection to the root bridge as a result of the root port or the link itself becoming inactive. In this example, we demonstrate this occurrence on switch B, for which connectivity to the root bridge or switch A is lost. Switch B will immediately be aware of the link failure and therefore immediately assume the role of root bridge. In doing so, switch B will begin to transmit BPDU containing its own bridge ID in the root ID and bridge ID fields of the BPDU that represents both the root bridge and designated switch. These BPDU will be received on the interface of switch C, but since switch C is receiving a better BPDU from switch A, the switch will largely ignore these BPDU. In addition, the port interface connecting switch C to switch B is considered an alternate port and therefore will not propagate BPDU to switch B, at least not immediately. Switch C must wait for the alternate port to expire based on the max age timer process. This will occur since switch C is no longer receiving a superior BPDU on this port containing the root ID of the root bridge. Following expiry, the port interface will switch roles from alternate to designated and begin to forward the BPDU information received from the root bridge to switch B, at which point switch B will no longer consider itself as the root bridge and transition its active port to a root port, since this port now represents the path back to the root bridge on which BPDU are to be received. Again, this process will take approximately 50 seconds as a result of the max age period and the need to perform state transition to ensure switching loops are not incurred during convergence. Where multiple LAN segments are connected between two switch devices and one segment is actively forwarding data while the other is operating as an alternate link, it is possible for a direct link failure to occur. We demonstrate here the case where the root port on switch B suddenly experiences a failure on either the root port interface or on the link to which the root port is connected. Switch B in such an instance will immediately detect that the failure has occurred and therefore does not wait for a max age period before initiating transition of its alternate port to become the new root port. This again, however, requires that the state transition process be performed to safely establish the new port for the forwarding of data. However, in this case, convergence is only limited to approximately 30 seconds based on the default forwarding delay timer for the listening and learning states. As part of the learning stage of the convergence process, the MAC address table of the switch will begin to populate with entries to define the path to destinations within the switching network. These entries are stored in the MAC address table for a period of 300 seconds or 5 minutes to avoid invalid entries being maintained. In the event that a change in the topology occurs, however, these entries may become invalid much sooner than expected. We show here two hosts connected via a converged spanning tree topology. Switch B is seen to have two entries in its MAC address table, showing association with host A and the existing path to switch A via interface gigabit Ethernet 0/0/2. Switch C, however, has experienced link failure on its root port and the path between host A and host B has been lost. The effect of this means that the segment between switch B and C must now become active, following which traffic forwarding can once again proceed. The theoretical problem faced, however, is that following convergence that took no more than 50 seconds, traffic between host A and B is not reaching its intended destination, since the old entries in the MAC address table have yet to expire based on the 300-second expiry period. As such, frames heading for host B from host A are forwarded via interface gigabit Ethernet 0/0/2, which leads down a dead-end path where frames are lost. In order to resolve the problem of invalid MAC entries within the spanning tree convergence process, a topology change process is invoked that handles the MAC entry timeout problem and relies on the previously mentioned TCN BPU to do this. TCN stands for Topology Change Notification and involves the transmission of a TCN BPU upstream via the root port along the path back to the root in the event that a need for a change in the topology occurs as a result of the link, port, or device failure in the network. Within the TCN BPU, there are two bit values, referred to as the topology change bit and topology change acknowledgement bit, or TCA. Once the TCN BPU reaches the root bridge, a BPU is generated by the root bridge and forwarded downstream. The TCA will inform the downstream switches that the root bridge has received the TCN BPU and transmission of this BPU can now cease. The TC bit, on the other hand, will inform the switches to reduce the timeout of the MAC address tables from 300 seconds to the equivalent of the forward delay timer, which is generally 15 seconds by default. In doing so, switches will clear all invalid entries from the MAC address table and ensure that entries will be relevant to the new converged spanning tree topology following topology change. We can demonstrate the result of this process here, in which case, following the shortened timeout period, the existing MAC addresses are flushed. From the perspective of switch B, the path to host A is relearned and the new path to host B via interface gigabit Ethernet 0/0/1 is updated in the MAC address table, thereby ensuring frames are not lost. Within VRP, we are able to configure one of three modes of STP. The version we have introduced here is the original form of STP, on which all other forms of STP are based. Using the STP mode command, it is possible to specify the form of STP that is to be used. Within VRP, this is set to MSTP by default, another form of STP that is covered as part of the more advanced training. In this instance, however, we will demonstrate the configuration of STP-based parameters. As part of optimal design of the spanning tree topology, it is necessary for administrators to be able to manually control which switch in the network should be positioned as the root bridge. This is effectively done by configuring the priority value of the switch. We can see from the example given here how the STP priority command is used, followed by the priority for the switch. It is important to remember that this value can only be applied in increments of 4096, and that the priority of the root bridge should be unique in the switching network as well as represent the lowest value. We may also wish to specify a backup root bridge in case of primary root bridge failure. This can be done by setting a switch to have a priority higher than the root switch but lower than all other switches in the network, providing some level of managed recovery in the event that the primary root switch is lost. This process of setting the root bridge and a backup to the root bridge can also be achieved using the respective commands of STP root primary and STP root secondary. If required, it is also possible to specify an alternative path cost standard to the default standard of 802.1t. We see here the use of the command STP path cost standard followed by the possible standards that may be selected. We may use this where working together with other switches that may only support alternative standards. Additionally, it is also possible to configure the individual STP path cost for each interface, which would effectively allow for a greater level of control over the actual spanning tree topology. However, in doing so, it is also possible that suboptimal switching paths back to the root bridge may be generated, and so care and planning should be taken before making any changes to the path cost for a switch interface. In this instance, however, we demonstrate how a path cost of 2000 can be assigned to the interface gigabit Ethernet 0/0/1. In addition to managing the spanning tree topology, it is also necessary to protect it against any changes that may either directly or indirectly cause the spanning tree network to reconverge, and possibly take on a form that results in suboptimal switching. In the case that the root receives a superior BPU as a result of misconfiguration of another switch or due to malicious intent, it will effectively result in the entire spanning tree topology reconverging. In order to prevent this, the designated ports of the root bridge can be configured with root protection. When the designated port of the root bridge receives a superior BPU, the root bridge, rather than relinquish its position, will cease temporarily to transmit BPDU downstream and will move into a listening state. Ports will, however, remain as designated ports. If no other superior BPDU are received for a period of time, the root bridge will reassume its role and resume transmission of configuration BPDU downstream. We can verify all of the configuration changes that have been implemented through the course of this section using the display STP command on switch A. The output provides information relating to the spanning tree topology, as well as provides statistics regarding the spanning tree operation. From here, we're able to verify that STP is the current mode being used, along with other information such as the bridge ID and the root ID that represent respectively the designated switch for the link and the root bridge for the spanning tree topology. The display format provides a standard layout for support of STP as well as RSTP and MSTP, and therefore some information such as the CIST, which refers to a common internal spanning tree, only becomes relevant when using MSTP. The highlighted priority value reflects the changes made to the priority of the root bridge. Since the bridge ID and root ID in this instance are the same, it can be understood that switch A is the root bridge. As the root bridge, all port interfaces should support a designated port role and be operating in a forwarding state. We can see this is the case when we take a look at interface gigabit Ethernet 0/0/1 of switch A. Other key points to take note of include the port priority that represents a priority of 128, and also the changes made to the port cost, which now represents a value of 2000. One final point refers to the protection type, which shows the root protection that has been configured in order to protect the integrity of the root bridge. In summary for this section on the spanning tree protocol, we have a couple of questions here. The first asks, in the event that a root bridge or switch temporarily fails in the STP network, the next viable switch will take over as the root bridge. What will occur once the failed root bridge once again becomes active in the network? Or once a valid candidate for the role of root bridge becomes active in the network, the candidate will immediately begin to generate BPDU to assert its dominance within the spanning tree topology. This will allow the switch that failed to regain its position in the spanning tree topology and also allow the original and what should be the optimal spanning tree topology to be reformed. The only problem with this, however, is the effective downtime that is caused as a result of convergence. What is the difference between path cost and root path cost? The path cost is the metric that is associated with the root port interface of a switch. The combination of the path cost of each switch along the switching path back to the root bridge is referred to as the root path cost. Its purpose is to determine the optimal path to the root bridge in order to ensure an optimal spanning tree topology is formed.